Hello everyone, this is my topic title, an SIR epidemic model with the both pass and pass vaccination on the newborn. I'm from Guizhou University of Finance and Economics. This is joint work with Professor Zhou. This is the outline, including introduction, remarks on models of single-species dynamics, structured population model and impassive effects, research model, and SIR epidemic model, some lemmas, the dynamics, conclusions, and simulations. Remarks on models of single-species dynamics. For models of single-species dynamics, most of the different differential equation models of population dynamics have been derived starting from the following simple format, this format. Kumgrove formulation. If one assumes that an individual's contribution to the change in population in unit time is denoted by a function C, f of n, defined suitably for all t greater than 0, n greater than or equal to 0, then one obeys from 1, the so-called Kumgrove formulation in this form. Massation formulation. Various choices of f, together with some ecologically perturbable assumptions such as the temporal constancy of the environment and density-dependent effects in F leads to several well-known ordinary differential equations of population dynamics. For instance, if f of Tn equals R, one obeys the Massation formulation. This formulation. Logistic equation. If one assumes f of Tn equals R minus R over k times m for some positive constants r and k, one gets the formula logistic equation, this equation. Structured population model and the impassive effects. Structured population models distinguish individuals from one another according to characteristics such as age, size, location, status, and movement to determine the both growth and death rate, interaction with each other, and with the environment, infectivity, etc. There is a very large and growing body of literature on these topics. It is known that many biological phenomena involving thresholds parasitic rhythm models in medical and biology. Optimal control model in economics, pharmacokinetics, and frequency modulated systems do exhibit impassive effects. Impassive differential equations have been introduced into population dynamics lately. Impassive equations have been studied in many investigations. Research model. In this paper, we consider an SIR epidemic model with both pass and pass vaccination on the newborn as follows: S1T, S2T, IT, RT, like this. Where S1 of T, S2 of T represent the numbers of the immature and the mature of the susceptible. I of T, R of T represent the numbers of the infectious and the recovered respectively. C is correlate of the mature susceptible turning into the mature susceptible. D1, D2, D3, D4 respectively denote the natural death rate of the immature susceptible, the mature susceptible, the infectious, and the recovered. Beta is the average number of adequate contacts of an immature infectious individuals per unit time. R stands for the recovery rate of the immature infectious individual. The mature susceptible is both passed with the intrinsic rate of natural increase and the density dependence rate of the mature susceptible denoted by A, B respectively. Delta S1 of t equals S1t plus minus S1t. Mu is the population of the successful vaccination, which is called pulse vaccination rate. We can obtain the following equivalent system of 5. This equation. Some lemmas. Lemma 1. There exists a constant big M greater than 0, such that S1t, S2t, it, rt less than or equal to big M for each solution S1t, S2t, it, rt of system 5 with t larger enough. We choose the following notation. Mu star equals this term. The subsystem of 6. If I of t equals 0, then we have the following subsistence of 6. We easily obtain the analytic solution of system 7 between passes as follows. S1t, S2t equals this. Considering the 4th, 5th, 7th, and 8th equations of system 6, we have the stroboscopic map of 6. The following two equivalence relations are found by calculation. The two fixed points of 9 are obtained as G1 of 0, 0 and G2 of S1 star, S2 star, where S1 star, S2 star equals this. Lemma 2. If mu greater than mu star, then the fixed point at G1, 0, 0 is globally asymptotically stable. If mu less than or mu star, then the fixed point G2, S1 star, S2 star is globally asymptotically stable. Lemma 3. If mu greater than mu star, then the trivial periodic solution 0, 0 of system 7 is globally asymptotically stable. If mu less than mu star, then the periodic solution S1t tilde, S2t tilde of system 7 is globally asymptotically stable, where S1t tilde, S2t tilde equals this. The dynamics. Global asymptotic stability. Theory 1. If mu less than mu star and mu greater than this term, then the disease-free periodic solution S1t tilde, S2t tilde 0 of system 6 is globally asymptotically stable, where S1t tilde, S2t tilde are defined by 10. The performance of system 6, theory 2. If mu less than mu star and mu less than this term, then system 6 is permanent, where S1 star, S2 star are defined by 10. Some simulations. The first simulation corresponds to the theory 1 in this paper. Another simulation. This simulation corresponds to theory 2 in this paper. Discussion. In this work, we consider an SIR epidemic model with the both pulse and pulse vaccination on the newborn at different fixed moments. All solutions of system 5 are uniformly ultimately bonded. The condition for the global asymptotic stability of this disease-free periodic solution of system 5 is given, and the prominence of system 5 is also obtained. Our results indicate that pulse vaccination later on the newborn plays an important role in eradicating the disease. It provides a reliable tactical basis for preventing the disease from spreading. There are some references. References 1, references 2, references 3, references 4, references 5, references 6, references 7, references 8, references 9, references 10, references 11. Thank you so much for your attention.